Okay, good afternoon, everyone. Okay, so welcome to our tutorial 3. Okay, so today's tutorial is covering a few things, correct? The concepts on the transformers, okay, the motors, as well as the op amps that we recently did. All right, so a few topics. All right, 14 questions, so I think it's quite okay, manageable. All right, so yeah, so before we get started with the tutorial, maybe it might be good to know, all right, that if you look at our schedule, all right, next week Monday is basically the last graded studio. All right, and basically after that you only have another 2 more studios, all right, which are not graded ready. Okay, and the rest of the sessions basically for you to do your project work. Okay, so it is technically almost near the end of the module, right, in terms of material. All right, of course the project is still something you need to work on. All right, so for the project you'll be doing what I think the video that you saw from the earlier batches as well. That means you'll be writing some software, okay, to control the M board, okay, to solve some challenges, okay, and so to solve those challenges you also need to build some hardware. All right, so that is where these topics on the op amps and what you're going to be studying, the IR sensors and so on, they'll be playing a part. Okay, so the project itself is doable. Okay, and since you have quite a lot of sort of contact time, all right, in the studio itself, then it is more than enough, I think, to prepare. All right, and every section has its own setup. Okay, so the center table, all right, where you currently used to maybe gather and discuss and so on, the center table is actually, we can remove the panel. Okay, so later you'll see we remove the panel and convert it into a maze. Okay, so that is why that center table is there in this section. Okay, so you have ample time, all right, and it's definitely manageable. All right, so of course I think the challenging part mostly is the hardware. So if the hardware is sort of designed well and it is working well, then I think there is no particular issue. But we will talk more on that, okay, as we start on it on week 10. Okay. Okay, so let's get started with the tutorial. Okay, so as usual, I will not go through all the material here. Okay, it's nothing new. It's basically the same stuff that you had from your studio sessions. Okay, so we will jump straight into the questions. Okay, and then from there we will actually be looking back at all these concepts. Okay, so the first few questions are on the transformers. All right, so for transformers, okay, basically you already sort of have a feel for it with the actual transformer, and you hooked it up and you've seen how it works. All right, of course this is just a very basic concept. Okay, there are a lot more I mean, if you look at EPP module, okay, the whole idea is not to go too in depth into the theory and all the very low level maths and derivations and so on, but to give you a very high level understanding and concept, so you can easily apply it and use it to do something useful. All right, so that is the whole idea of EPP. So even though transformers right now seems as a very easy topic, all right, there are still a lot more things when you go more in depth into it. Okay, so for question 1 over here, what we have is we have a transformer. Okay, so if I were to draw it out here, okay, so we have a primary, okay, and a secondary. Okay, and you are given that the primary voltage here is 65 V RMS, All right, and in terms of turns, you have 60 and 90. So you have 60 here and 90 here, and you're supposed to find the Vs. All right, so you just directly plug in the formula. Vs over Vp is equals to Ns over Np. Okay, so put in those numbers. Vs over 65 equals to 90 over 60. So Vs will give you 97.5 VRMS. Alright, so very straightforward. Okay, just using the formula directly. Alright, to solve this question. Okay, so I'll not spend too much time on this. Okay, I think it's quite straightforward. Similar question 2 is also sort of plug and play the formula only. Alright, so it's the same thing. You have a transformer. Okay, in this example, you are given that Vp is 25 RMS and Vs is 90 RMS. Okay, the secondary windings is 36. You're supposed to find NP. All right, so you can do the same thing. Okay, so Ns over Np is Vs over Vp. So 36 over Np gives me 90 over 25. So Np will give me 10. All right, so again, just directly using the formula alone. Okay, so nothing special there. Okay, question 3. So in question 3, we are given a transformer, all right, where we are told the secondary and primary voltage, okay, and we are asked to find the primary voltage for another secondary voltage. Okay, so basically it is just a ratio, correct? Question of ratio. So Vp to Vs, what you currently have is 30 is to 100. Okay, so if I want to find for Vs as 225, then by a simple your ratio in maths, okay, you just do this, correct, and then you'll get it as 67.5 VRMS. Okay, so you're just finding the ratio, okay, from one voltage to another voltage, and that's it. All right, so I think the first 3 questions here are fairly straightforward. Okay, no need to spend too much time on it. Okay, question 4. So question 4 is similar. All right, only thing is we have now a load attached to the secondary side. Okay, so this load is a series RL load. Okay, so it's a series RL load. So what happens here? So your V peak here is given as this 325 with a phase angle of 0. All right. So once the transformer is working, your secondary side you will generate a voltage. All right. Again, there is no phase difference. So primary side 0 degrees, second side also 0 degrees. Okay, for the voltage. Okay, so for the current side, all right, we know that there will be a current generated since we have already have a closed loop over here. So this current Is will be given as Is with a magnitude and a phase angle. Okay, so that is the current that is flowing in the secondary of the circuit. So now we have 2 components, R and L. All right. So if you look at it, your VR, okay, is actually given as VR magnitude angle with a theta over here. Okay, so since we do not know the angle, okay, so we just keep it as theta. So we can say that is 6 angle theta. Similarly, you can do the same thing for the inductor over here, VL. So for VL, it is basically I multiplied by XL or ZL, the inductance. Correct? So if you put it in terms of phasor, okay, what you will get is this as magnitude of I with a particular angle theta. And this will also be a magnitude of the XL. And as you know, inductor, the voltage leads by 90 degrees. Okay, so the full expression for this Okay, if you look at it, is XL is J omega L. Okay, J omega L. So if you just take the magnitude of it, okay, so you know the J is already factored in the 90 degrees. So it become omega L and I. So that will be the magnitude. And then the whole phase angle will be theta plus 90 degrees. Okay, XL is ZL. Okay, I'm just used to using the other notation. Okay, so the reactance or impedance, usually people use two different notation. Okay, so similarly for capacitance, the same thing. The reactance. Okay, so this is J omega L. This is 1 over J omega C. Okay, so I know the nodes generally use Z. Okay, but I'm just used to using the X. Okay, but it's the same thing. Okay, most books usually have a mix of both. Some will use X, some will use Z. Okay, now that is of course the full sort of relationship between the uh, current and the VR and the VL. Okay, the voltage drop across both the components. Okay, now if you were to sort of represent it in a phasor form, okay, so you can say that your VS is okay what you are interested in finding, correct? Your VS. So you know VP, you want to know VS, because if you know VS already, then you can relate it to find the ratio of NP over NS. So what you want is the VS. Okay, but we know that VS, okay, from your studio as well, you know, is actually a phasor combination of your VR and your VL. Right, you know that is a phasor combination of VR and VL. So since VR and VL is both given to us, so this magnitude is 6. Okay, and this magnitude here is 8. So VS here is basically the 6 square plus 8 square square root, which will be 10. All right, so with that, you can actually directly just find the ratio here. So NP over NS is given as, here is 325 over 10, which is 32.5. Okay, so the relationship, okay, of the VR and VL, okay, the phasor relationship adds up to the VS. Okay, so we have seen this in the studio, all right? So that is basically what you need to apply here to solve this. Okay, so it's the same ratio formula only. Okay, the only difference is in this case you have a load which is complex in nature. Okay. Okay, question 4. So for question 4, basically, what you, no, sorry, this question 4 we did. So these are all the steps. Okay, question 5. Question 5 is basically to derive that formula, okay, for the voltage ripple. Okay, so in the studio, we gave you the formula, all right, and we just asked you to sort of accept it first, all right, and then now we're going to look into the sort of way in which the formula can be derived. Okay, so if you look at the waveform that we get is a full rectified waveform, all right, so we know that what is happening is, all right, as your waveform, the signal rises up, okay, there'll be a point where the capacitor charges, okay, and when your voltage drops below the capacitor's voltage, it will start to discharge. It will start to discharge. Okay, and then because of the next rectified waveform that comes in, then the charging cycle starts again. Okay, so this is basically what we sort of see. All right, so we will make some definitions first, all right, based on the circuit. So the circuit is basically this connected to your capacitor and your load. Okay, so the first thing is let V load be the average load voltage. Okay, that means what the load is going to see. Okay, so the current is then defined as V load over RL. Okay, so these two are the first two definitions. And we also know that the waveform or the pattern repeats itself every t by 2. Okay, so every t by 2 the waveform repeats itself, so the pattern will repeat. Okay, so now let's look back at some concepts of the capacitor. So the principle of the capacitor states that the change in the voltage is related to the change in the amount of charges over the capacitance. Okay, so this formula you can look back at the handout for the capacitor studio. Alright, so this is one of the basic formulas of capacitance. Okay, how the voltage changes. Okay, it is directly proportional to the amount of charges. Okay, that are sort of stored in the capacitor. Okay, over the actual capacitance. So that relates to the change in the voltage across the capacitor. Okay, so now the next thing is this delta V over here. Okay, we are going to again make some sort of assumptions, okay, to make our analysis easier. All right, so we can see that the whole cycle here, from here to here, is actually two parts to it, T1 and T2. All right, but if I want my delta V to be small, okay, if I want my delta V to be small, then effectively what am I doing? I'm trying to stretch this closer and closer to the end of the entire cycle, correct? So the voltage ripple becomes as small as possible. All right, so in order for delta V to be small, that means the voltage ripple to be small, then we can make a sort of approximation that T1 is very close to T by 2. Yeah. Yeah, Q is the charge and C is the capacitance. Okay, so for the delta V to be small, okay, the voltage ripple to be small. If I relate back to this relationship between T1 and T2, I want T1 to be stretched as much as possible and T2 to be small as possible. So we approximate that T1 is very, very close to T by 2. That means T2 is very, very small. Okay, so that is the first sort of approximation we will make. Now, the next formula we will look at is the IT, which is dq by dt. This is also from the capacitance or the inductance sort of formula, all right, where the current is also the rate of the change of the charge, okay, over time. Okay, so so in the capacitance handout, you also see this formula where the current flow is also related to the rate of flow of charges. Okay, so this is another formula that we know, we have seen before. So current is the rate of flow of charges. Now, if we apply this to the inductor formula that we have here, which is okay, so we don't apply this here first. Okay, we apply this back to the concept of dq as change of charges and dt is basically the t by 2. Okay, so what we are saying here is the current that is now going to flow in, okay, to the load, okay, to the load is proportional to this, correct? Current flow is rate of flow of charges. So charge is delta q, and now the time is defined as t by 2, right? Because that is the entire time where the capacitor is sort of charging or discharging. All right, so that is the total current that is now going to flow into the load. All right, so now that we have all this, okay, we come back to this formula over here. Okay, so now let's look back at this and try to put in whatever we have. Okay, so what is delta Q? Okay, so if I rearrange this formula here, I will get that delta Q is IL multiplied by T by 2. So delta Q is IL multiplied by T by 2. Okay, over C. All right, that's the first step. Now the next step is what is IL? IL is given by this VL over RL. So this will be VL over RL multiplied by so T over 2 is the same as 1 over 2F. Okay, 1 over 2F and multiply by 1 over C. All right, and that is basically the entire expression here. So this is actually the full expression that you used in the lab. All right, so let me just recap again. So the first step we do is we take the load voltage, all right, and say that VL will be defined as the average load voltage. And then we take the average load current as VL over RL. All right, so that is the first step. Okay, and then we look at how the capacitance is derived. So we are related to the voltage. So we know that the change in the voltage is related to delta Q over C. Again, this is from the capacitance handout. Okay, the slides you can get that. Now we come back to the concept of what is the time duration. So we know that it is sort of charging and discharging, but the discharging is we want it to stretch as much as possible, all right, so that the ripple is as small as possible. So we take that the full duration is just going to be T by 2. Okay, so that will be the full duration that we are going to analyze, okay, related to T1. Okay, and then the last step is we look back at this relationship of current. So current is basically the rate of flow of charge. Okay, so the current can now be written as delta Q over T by 2 because delta Q is the total amount of charges flowing and the time duration is T by 2. So that is what we are analyzing at the moment. All right, so now we put everything back into the first expression over here. And then we relate it to find this final formula here. Okay, so this is basically the sort of thought process towards how we derive this expression. Okay, again, it's not 100%, right? Because we make some assumptions, right? We make some approximations, right? But this sort of gives us a very close value. So if you remember in the studio, the value that you calculate here and the value that you sort of measure is quite close. Okay, it's quite close. So this approximation is good enough for us to know the voltage ripple that you will get, okay, at the output side. Okay, so this sort of gives you a better closure, okay, to how we actually use or derive this formula and used it in the studio. Okay, so again, all of that is over here. Okay, question 6. Question 6 is just directly plugging in the values. All right, so you are given all this information: the load, the voltage, frequency in the radians, okay, the capacitor, and so on, and find the voltage ripple. So you just plug everything into the formula over here. All right, and the only thing is you just need to be careful that the F here has to be in hertz. So if you're given it in radians per second, so that is in so you need to divide by 2 pi. So that is 2 pi F is equals to 100 pi. So F is 100 pi over 2 pi. Okay, so you just need to make sure that the frequency here is hertz. Okay, other than that, the rest is just plugging in the values and you can get the voltage ripple here. All right, so this one I think is quite straightforward. You just plug in the values to directly get the answer. Okay, so question 7 is also an application of this. Okay, that means they are giving us this information. All right, and we are asked to find the minimum value of the capacitor in order to achieve a voltage ripple of lesser than or equal to 0.5. Okay, so let's put in the value. So we know that the voltage ripple is given by VL over 2F RL and C. Okay, and I is actually VL over RL, correct? So VL over RL over here, I can simplify it to just put it as IL over 2FC. All right, and if I put in the values, so the current here is 0.2 over 2 times 50 times C, and this will give me the delta V, and I want the delta V to be smaller than or equal to 0.5. Okay, so then the rest is just your maths. All right, then you can solve it to be greater than or equal to 4 millifarad. Okay, so that will be the final answer here for question 7. So you're just applying the same formula, all right, but now we have given a requirement for the peak to peak ripple, all right, and you're supposed to find the specific capacitance or the minimum capacitance to make sure that you're able to fulfill this requirement. Okay, so that is question 7 here. Okay, so that basically wraps up the part on the transformers, okay, studios that we did. Okay, so far any questions? Anybody have anything you want to ask or clarify? Okay, so there's a question here. Why is the frequency? Okay, because the formula, okay, that we are using, okay, the F is frequency in hertz. Okay, so this is supposed to be in hertz. So if they have given you in radians per second, then you need to convert it to hertz. That's why you need to divide by 2 pi. Okay, because if you look back at the way we derive the formula, this delta T is based on the time. Correct. So when we did the reciprocal, it will be 1 over F. Correct. So it is the direct relationship between the time and the frequency. Okay, so for question 4, the vector diagram. Okay, so this vector diagram is basically because your source, okay, if you remember your studio, okay, when you have a complex circuit, all right, with the AC signal, okay, your components will all, the phasor diagram will all add up, okay, for the Vs. So when you have a source voltage, okay, whether it's resistor or inductor or whichever way. So if you remember rightfully, what you have is in your studio, you will have your VR somewhere here maybe, and you have your VL, okay, and that will be your Vs. Correct. So basically, the Vs is a combination of VR and VL, but it has to be in phasor form. Okay, why phasor form? Because your AC signals are always changing, correct? So your KVL, okay, concept only works if you look at it in the phasor notation. Okay, because you need to look at it at a particular snapshot of time. So that only works with the phasor notation because now you consider the phase difference across the various signals. All right, so it's the same concept we did in the studio, all right, where the Vs is the combination of VR and VL, but taking the angle into consideration. Okay, so you just apply the Pythagoras theorem, okay, to get the actual Vs value. Okay, so let me move on to question 8 first. Okay, so the next few questions are on the motors. Okay, so for the question 8, so we are given that we have this PMDC motor, 12-volt source, no load speed at 3,800 RPM and stall torque. Okay, so now let's okay, so we are asked to find this. If now running at 2,500 RPM, find all of this. All right, so let's look back at the formula that we have. Okay, so let me write down the formulas that we have first. IM is equals to Vm over Rm minus Ke omega over Rm. All right, so this is the formula that we have. Okay, we have a few others, but if you look at what we're supposed to find first, we're supposed to find Im. Okay, so to find Im, okay, I can use this formula, correct? So to use this formula, I need to know these parameters. All right, Vm I know. All right, omega I know because I told the RPM. So from that I can find the omega. So what is missing? What is missing is I need to find the Ke. I need to find the Rm. So these are two parameters that are missing from this expression. So I need to find it. Okay, so of course once I find that, the rest of it is just putting in the formulas only. All right, so the step is always finding the missing parameters. Okay, the rest of it is just plug it into the formulas, you'll get the answers. All right, so let's understand the concept first. So the first one is no load. Okay, so when you say no load speed, what does that mean? So when no load speed means we say that the current in the motor is approximately 0. Okay. Okay, why the current is 0? Because the torque by the shaft is 0. Okay, so this relates back to the another formula, which is T shaft is equals to KTIM. Okay, so if I am running and no load, then you say and no load the torque is 0. So if the torque is 0, then the current is also 0. All right, so that is the first understanding you must get when we say that it is a no load condition. Okay, so with that, I plug in back into my expression here. What will happen? Okay, so if I plug this information that Im is 0, okay, back into this Im expression, okay, what I will get is Vm over Rm minus Ke omega over Rm will be equals to 0. All right, then all you have is Vm equals to Ke omega. So Ke is equals to Vm over omega. All right, so the omega has to be in the radians per second. So what we are given here is 3,800 RPM. Okay, so I need to convert it. So the formula is also given in your notes. So to convert it to the omega, it is 2 pi times RPM over 60. Okay, so that will give me the answer in radians per second. Okay, now so in our case here, when you convert, you will get an answer of 398 radians per second. Okay, so now if I put in the values here, Vm is 12, okay, over omega, which is 398. Okay, what I'll get for Ke is 30 millivolt over radians per second. Okay, so that is the first thing. We have found Ke. All right, and from your handout, you also know that for this kind of motors, we take it that KE is equals to KT. Okay, so these are all the formulas that you must take note of. Okay, so this 30 is also applicable to KT. Okay, both KT and KE are the same. All right, so using the no load condition, no load information, we are able to now derive the KT, the constant. Correct. So one part of it is solved already. So this one is solved already. So what is remaining is the RM. So we need to find RM. All right, so the next information is the stall torque. Okay, so now let's look at the stall torque information. So what we have is stall torque is 30 milli Nm over here. So at stall, okay, we can now look back at the this formula again, which relates the torque to the current. All right, so we can say that based on this information over here, we can now say that the torque of 30 milli is equals to KT and IM. And KT is also 30 milli. All right, so this is also 30 milli. Okay, so from there we can say that IM is equals to 1 ampere. Okay, so now we have found the current. All right, so what is the RM? When stall condition, okay, under stall condition, your motor is not spinning. Correct? Under stall condition, your motor is not spinning. That means your omega is 0. Okay, omega is 0. So under stall, okay, the omega is 0. It's not spinning. So now if I put back into my current formula here, I can say that IM is only equals to Vm over Rm. Okay, because the omega is now 0, the second part of the expression is no longer there. Okay, with that I can find Vm. So I can find Rm. Okay, this will be V over I, so I'll get 12 ohm. Okay, so as you can see now we have found Rm. Okay, we have found the Ke. So with that, I can now I already have all the unknowns. Okay, so the rest of the A to F is just plugging in these values into the formulas. Okay, so let's just go ahead and do that. Okay, so for the first one, okay, torque is this TSH is just the shaft torque. You can apply this expression at any time. So if you're given the stall torque, then you apply it, then you're getting the current or the KT at stall time. Okay, if it is not stall, then the formula still holds true. Right? You just apply this formula given the information that you have. Okay, so the stall torque, or whether it is not stall, whatever torque information you have, you can still apply this formula here. Okay, and it will still hold true. Okay, so now let's plug in the formulas to solve A to F. So now what we need to do is we need to find these answers when we are now running at 2500 RPM. Okay, now we're running at 2500 RPM. So at 2500, okay, 2500 RPM, the first thing is we want to convert it to omega. 261.8 radians per second. Okay, now the first part A, the current. So I can plug in my formula. Current is Vm over Rm minus K omega over Rm. So I'll get 12 over 12 minus 0.03. So in this case, the omega is for this 2500 RPM over 12, I will get 0.346 ampere. Okay, so that is part A. Okay, then the torque at 2500 is basically the KTI. Okay, but KT, as you know, is 0.03, and the current at 2500 is what we just saw, 0.346. Okay, so that will give me 10.4 millinewton meter. All right. Then the next one here, C, E, the back EMF voltage. Okay, is KE omega. So this is another formula from your handout. So KE and KT are the same. So 0.03 multiplied by the omega, which is 261.8. So I get 7.85 volts. Okay, so the question, how many significant figures? I think if most of the time you usually keep 3 significant figures till the final answer. I think that should be enough. All right. Okay. I mean, the answer that you get if you use more is usually closer. All right. And more accurate. But I guess if you think of it, if answering a question, I think 3 significant figure, you keep all the way, I think it's fine. Okay, the D is PE VM times I. So the D is basically asking you for the electrical power consumed. So that is the total voltage times the current. So that will be 12 times 0.346, and that will give me 4.15 watt. Okay, the power consumed by the shaft, that is torque of the shaft multiplied by the omega. Okay, so this is also another formula inside your handout. So that would be 10.4 milli times 261.8, and that will be 2.72 watt. Okay, and for the last one here, power loss. Okay, so the power loss is basically the loss within the internal resistance, okay, of the motor winding. So that will be current I square R. Okay, so that will be 0.346 square multiplied by 12. So that will give me an answer of 1.44 watt. Okay, so there's a question, when you say no load current, you're assuming no friction torque. Yeah, so the concept is that when your motor is initially when you initially start to run the motor, there would be some initial torque to overcome. Correct, but once it is considered free running, right, that means there's no more need to overcome that torque. Okay, then the actual current is almost close to zero. Okay, so the torque is no longer there, correct, because it's already in a free running mode, and we say the current is almost close to zero. So that is the sort of simplification you can assume. Okay, when we say no load speed. Okay, the torque is zero and the current is zero. Okay, so those are all the steps for question 8. All right, any questions on this? Okay, so let me move on first. Question 9. No load current means no torque. Okay, we assume that the current is 0 because the torque is 0. Okay, so question 9 is sort of a follow on, okay, where the load condition is unchanged. The load condition is unchanged, but now we want to change the speed of the motor, correct? So the new desired speed is 1500. Okay, so the first thing is let's just draw it out here. So you have your resistance plus your motor and the shaft, okay, and you're spinning at a particular speed, okay, with a torque, okay, and at the same time there is a back EMF voltage here. All right, so this is what you have. Now when you say load condition unchanged, okay, when you say load condition unchanged means the torque is the same, because the load is the same means the torque is the same. Now if you look back at the formula, we say that this means that the torque is KTIM. So if the torque remains unchanged, the current remains unchanged. Okay, so the current that we had from the previous expression, okay, the current here 0.346 is the same. Okay, the same current is going to flow through the motor right now. Okay, so this current here IM is the same as before. Okay, it remains unchanged. Okay, so the rotor current is the same. Now let's look at the required VM. Okay, so what is the voltage I require now to drive this load? Okay, the motor with the load at 1500 RPM. Okay, so when this current is flowing in, 0.346 ampere is flowing in, okay, what will happen? I will have a voltage drop across here and across the EB, correct? So we know that the resistance is 12, correct? We already know that from just now. So this voltage drop here, okay, across the resistor is 12 times 0.346. So that will give me okay, I forgot the actual value. Okay, but that is the voltage across the resistor. Then EB is given as KE multiplied by omega. So there's a back EMF voltage, okay, when your motor is running. So the motor is the same, so the constants remain the same. All right, so that will give me 4.71 volt. All right, so by KVL, okay, by KVL, you can say that the VM here is actually your VR plus your EB, which will give me 8.86 volts. Okay, so in order for me to run this motor, okay, with that same load, okay, but with a lower speed than just now, okay, 1500 RPM, I need a voltage of 8.86 volt. Okay, so that is now the voltage requirement, okay, for the same load, but now at a reduced speed. Okay, so now that my voltage requirement has reduced, okay, but my DC source is still 12 volt. Okay, it's still 12 volt, but I don't need 12 volts. Okay, I only need 8.86 volts. So I can now use PWM. Okay, so the whole idea of PWM is to cycle the signal, correct, in a particular on-off sequence, so that the average voltage is what I want. Okay, so what I want is 8.86, but the maximum here is 12 volt. Okay, so the total duty cycle that I need is 8.86 over 12, which will give me 73.8%. Okay, so that is the total percentage I need out of the total full 12 volts. Okay, because I only want 8.86. All right, so with that, okay, you can now go to part C, all right, which says what is the on-off frequency, timing duration if the frequency is 5 kilohertz. Okay, so we know that this is the on and this is the off, and this total period here is going to be 1 by 5k, which is 200 microseconds. Okay, and since I want the percentage of the total to be 73.8%, so 73.8 of the 200 microsecond is equals to the 147.6 microsecond. So that is the T on. Okay, and then the 200 minus T on will be equals to 52.4 microsecond, and that is your T off. All right, so basically the setup is the same as the earlier question, correct? But now since you want a reduced voltage, okay, instead of directly having a DC source connected to the motor, we use the PWM approach, okay, to provide the required voltage. So instead of having 100%, we now bring it down to 73.8%. So when that happens, you will get 8.86 volt as your VM. Okay. T is the total period is 1 by F, right? The frequency here is given as 5 kilohertz. Okay, so the PWM period is 200 microsecond. Okay, so out of the 200 microsecond, then we want to derive the on and off. Okay, so this 5 kilohertz is here, given here. Okay, then the last two, D and E. So for D, electrical power consumed. So the power consumed is the same, PM multiplied by IM, which will be 8.86 multiplied by 0.346. So that will give me 3.07 watt. Okay, now the power loss. The power loss is the same, I square R. Okay, and if you look at it, the I has not changed. Okay, so I has not changed, multiplied by the R, you'll get the same answer as before. Okay, so the power loss is the same, okay, because the current is the same. All right, so the current is the same, then the power loss experienced by the motor is still the same. Okay, so in this question, basically what we're trying to see is, okay, the same setup, okay, but now I reduce the speed requirement. So that translates into a reduced voltage requirement. All right, and I can fulfill that voltage requirement by using the PWM approach to my DC signal. Okay, so that is basically what this question lets us do. Okay, so let me finish question 10, all right, and then we will go for a break. Okay, so question 10 is a motor with a fan. The load torque is given, all right, and KT and RM and so on. So they ask us to find the speed of the fan. Okay, so the speed of the fan is basically given as omega, correct? So you're supposed to find omega, and we are given an expression for the torque. Okay, so the formula we have for torque is torque of the shaft is equals to KTIM. Alright, so that is the formula we have. And IM is also given as VM over RM minus KE omega over RM. So these are the formulas we have, right, to relate the torque and the current and the other information here. So let's put in everything here, okay, and then we see what we have. So if this is my full expression for IM, and I take this and I put it inside here, okay, so I can say that the torque of the shaft is now given as KT multiplied by this whole expression, VM over RM minus KE omega over RM. Okay, and now let's put in the values. So that is given as 2.42, okay, 50 over 0.2 minus 2.42 omega over 0.2. So this is the torque of the shaft. And we are given an expression for the torque of the load. All right, but if you look at your question, they have said that the fan is coupled tightly, okay, to the load. Okay, so the reason when we say that the load and the shaft are tightly coupled together, that means we take that the torque for the load is the same as the torque for the shaft. All right, so that implies that this is the same as the torque for the load. Okay, they are both the same. All right, so what you can now do is you can equate both of them together. So you can say that 0.005 plus omega plus 0.001 omega square is equal to this entire thing over here. Okay, so this one, when you expand and everything and you simplify the numbers, you will get something like this: 605 minus 29.3 omega. Okay, then so basically what you have now is sort of a quadratic expression, correct? So you just simplifying. So I mean, if you want to just put everything in your calculator and solve it, that is also fine. Okay, so these are just the numbers if you want to do it a few more steps. All right, and if you solve this quadratic expression, basically you will get two values, correct? Or negative 29371. Okay, so definitely omega is a positive number, so we take this, okay, which translates to 197 RPM. All right, so the rest of it I think is just maths. Okay, the first part here is the important concept that we want to find omega, all right, and what is the information given? We are given information for the torque. All right, so we know this formula for the torque. All right, and the other formula where there is also omega inside, okay, with other parameters that is given to us is this. All right, so we put that into the torque expression, and since the load is closely coupled with the shaft, then we say that the torque experienced by the load is the same as the torque experienced by the shaft. All right, and by equating them together, then you just solve the quadratic expression. You'll find the speed of the fan. Okay, so yeah, that is basically question 10, all right, which also sums up the motor related questions. Okay, so again, T load is equal to T shaft because of the question which says that they are both tightly coupled together. Okay, so when they are coupled together, basically means that the load is directly connected to the shaft in a way that there is no loss. So the torque is exactly the same. All right.
Okay, so I think now is a good time to take a break. All right, so now it's about 3:05. Let's take a 10 minutes break. Okay, 3:15. I'll see you back here, and then we will look at the remaining op-amp questions and anything else that you want to ask as well. Okay, so let's go for a 10 minutes break. Okay, then we'll come back and we'll do the rest of the questions. Okay, so let's carry on. Okay, so the last few questions are all on the op-amp. Okay. So though we introduce you to the two main basic configurations, inverting and non-inverting, okay, in the studio, op-amps are actually quite a useful device. All right, they can actually be configured to do a lot of things. All right, generating waveforms, amplifying, inverting, summing, so finding difference and so on. All right, so it has a lot of very useful applications. All right, you will see some of those in the subsequent studios. All right, and probably in other modules as well. Okay, so to solve these remaining questions, basically you apply the same concepts of KCL, Ohm's law, and so on. Okay, but at the same time applying the op-amps golden rules. All right, which basically says that your V plus is equals to V minus, and your current flowing into the op-amp terminals is 0. All right, so if you look at this first circuit here, they ask you to calculate the overall voltage gain of this amplifier circuit. Okay, so to find this, all right, you just need to apply the principle, okay, which is V plus is equals to V minus. Okay, and the current into the plus and the minus terminal is 0. Okay, so over here what you have is, if V plus is connected to VE, which is 2.6 volt, then the voltage here is also 2.6 volts. Okay, if this is 2.6 volts, then because the other end of the resistor has a ground, then you can calculate this current. So this current over here, I, is given as 2.6 over 56K, and that will give me 46.4 microamps. All right, and since we know that there is no current flowing into the terminal of the op-amp, so this 46.4 microampere must also be the same current that is flowing here. Correct, because there is no current going into the negative branch. So the full 46.4, you can say, is also the same current flowing from the V out into the 22 kilo ohm. All right, so with that, you can now calculate the voltage drop across the 22K resistor, which would be 46.4 micro multiplied by 22K, and that will be 1.02 volts. Okay, so basically what you have is, at this point you have 2.6 volt, and then you have another 1.02 volts. Okay, drop across the 22K resistor. So the voltage at the top here, which is V out, will be 2.6 plus 1.02, which will be 3.62 volts. So that is basically the output voltage that you will get. Okay, so with that, you can now calculate the gain. So the gain is given as V out over V in, which is 3.62 over 2.6, which is 1.39 volt over volt. Okay, to convert this to decibels, all right, to convert this to decibels, basically all you need to do is do a 20 log of it. Okay, you'll get an answer of 2.86 dB. Okay, so for voltage gain, okay, you will take a
20 log of the actual ratio, and that will give us the answer in the decibel form. All right, so that is how you calculate this gain here for the circuit. All right, so the concepts are the same, okay? The Ohm's law and KCL based concepts only, all right? But you just apply it together with the understanding of how the op-amp works. All right, so let me move on. Okay, so for question 12. So question 12, again, the same thing. Now you have sort of two separate circuits, okay? Or two op-amps connected together. So you can sort of break it up into two circuits here. Okay, so the first stage is, again, as before, this is 3.6 volt. All right, so with this being 3.6 volt, then you can calculate this current here as 3.6 over 15K, and that will give me 0.24 milliampere. Okay, and then with that, I can calculate the voltage drop across here. So that will be the voltage drop across the 10K will be equals to 0.24 milli multiplied by 10K. So that will be 2.4 volts. So this will be 2.4 volts. So that means the voltage here at this point will be 3.6 plus 2.4, which is equals to 6 volts. All right, so that is basically the first half of the circuit. Okay, so for the first half of the circuit, all right, they ask you to calculate the gain and stage for each part of it. So for the first half, you can calculate the gain as 6 over 3.6, and that will give me 1.67. And you do a 20 log of it, you will get 4.45 dB. Okay. Now for the second stage, so for the second stage, you get 6 volts as the input. All right. At the same time, you can see that this is ground. Right, V plus equals to V minus. All right, so with that, you can take it as the current flowing here is the same current is going to flow here. All right, so that current is given as 6 minus 0 over 33K, okay, which is 0.182 milliampere. Okay, and that same current is now going to flow through the second 56K resistor. So it means the voltage drop here will be 0.182 milliampere times 56K, which will give me 10.2 volts. Okay, but as this is 0, okay, this point here is 0, so it's a 10.2 volt drop from 0, correct? So the total V out over here will be equals to 0 minus 10.2 volt, which will be negative 10.2 volts. Okay, so your V out is negative 10.2, your input is 6. All right, so for the second stage, the gain is given by negative 10.2 over 6, which should be negative 1.7 volts by volts. All right, and if I were to convert it to decibels, it will be 20 log to the base 10. All right, so you can't do a log of a negative number, so you always take the absolute value of it. Okay, so that will give me 4.61 decibels. Okay, so as we mentioned before, the negative is not a indication of a loss. Okay, the negative, it just means that the signal is inverted. So the output is the inverted version of the input, but with a scaling factor. All right, and to calculate the overall gain. Okay, so to calculate the overall gain, there is two ways. Okay, so the overall gain. Okay, so you can either take gain 1 multiplied by gain 2, all right, or gain 1 in decibels plus gain 2 in decibels. Okay, you will get the same answer. All right, so if I take the first approach here, A1 times A2, I will get an answer of 1.67 multiplied by negative 1.7, it should be negative 2.84. Okay, if you take 2.84 and you find the decibels, you'll get 9.06, which is the same as saying 4.45 plus 4.61, you will get 9.0607. You might get 06 or 07 depending on how much you round off along the way. Okay, so the overall gain, you can either multiply both the ratios or you can add up both the decibels. Okay, either way you'll get the same answer. Okay, so this is basically a two-stage amplifier. All right, and in some cases, again, depending on the circuit you're trying to build, you may have many more amplifiers in parallel. Okay, depending on maybe they need to have different gains. Okay, this 6, there's a question here, this 6 minus 0. This 0 here is because of this ground. Okay, V plus is equals to V minus, correct? So the current flowing here is the Ohm's law, right? 6 minus 0 over 33K. Okay, so we are applying the principle that V plus is equals to V minus. So V plus is ground, means the point at V minus is also ground. Okay, so that is how we get that. Okay. Okay, so this circuit is considered two parts, all right, because we have one circuit with a particular V in that generates output, okay, which is here, and then the circuit is then, that signal is then sent to the second half of the circuit. All right, so the analysis we do on the first part of the circuit is to find out the voltage that is generated at the output of the first op amp. Okay, and after that, what we do is we apply that input to the second op amp. Okay, so the analysis, okay, is done separately. So the first half we do to understand what is happening in the first op amp first. All right, and in the second op amp, the ground, okay, is connected to the negative. I mean, the positive is connected to the ground. So because of that, the negative is also considered grounded. Okay, V plus is equals to V minus. Okay, so that is basically question 12. Okay, so these are all the steps you can go through when you get the slides. Okay, so for question 13. So let's look at question 13. So in question 13, we are also asked to calculate the voltage gain. All right, so for the voltage gain, let's do the same analysis. Okay, so V in is connected to the positive. So similarly, that means this point here is also considered V in. All right, and with that, you can find this current. So this current here, I, is equals to V in over R1. Okay, so that is the first thing we can do. Now let's take this node over here and let's call this V2. All right, so now this current I that is flowing through R1 is the same current that is also flowing through R2, correct? Because there's no current going to the other branch, which is the op-amp terminal. So this is also I. So the voltage drop across R2 is I multiplied by R2. Okay, IR. Okay, so that is the voltage drop across the R2 resistor here. Okay, so with that, you can say that V2 is given by V in plus IR2. Okay, the voltage at this terminal, the other end of the resistor, plus the voltage drop across the resistor. Okay, so I can simplify this. So V2 is V in 1 plus, sorry, it's R2. Okay, so V2 is given as V in multiplied by 1 plus R2 over R1. Okay, so the concept is V minus is also V in. So the current through R1 is V in over R1. Okay, and since the same current is also the current that flows through R2, the voltage drop across R2 is IR, I multiplied by R2. Okay, so the voltage at V2 is V1 plus the voltage drop across R2. Okay, so that is how we get this. Okay, the voltage at the point for the node V2 is V in plus I multiplied by R2, the voltage drop across R2. Okay, so now we have expression for V2, okay, in terms of V in. Okay, in terms of V in. All right, so what we want to find is this, right? We want to find V out over V in. All right, so V in is on, again, the one part of the circuit, and we want to bring that relationship of V in through the components to another part of the circuit where we can relate it with V out. All right, we want a relationship between V in and V out. So now to bring V out into the picture, what we can do is we can look at this node over here. Okay, so as you can see here, this plus is grounded. That means this point is also grounded. Okay, and we can now apply KCL to this node over here. All right, to say that, for example, all the current flowing in or flowing out is 0. Okay, so of course this branch here, okay, from the op-amp side, there is no current flow, so there is nothing on this branch, so only have the branch from V2 to the node and V out to the node. Okay, so with that, if you apply KCL to this node over here, okay, what you will get is V2 minus 0 over R3 plus V out minus 0 over R4 is equals to 0. Okay, there is no current in the third branch because that is the op-amp branch. Okay, so you can say V2 over R3 is equals to negative V out over R4. Okay, and since we have an expression for V in already, so for V2 in terms of V in, so I can put it as V in over R3 multiplied by 1 plus R2 over R1 equals to negative V out over R4. Okay, then the final step is you just rearrange everything. You get negative R4 over R3 into 1 plus R2 over R1. Okay, so the idea is basically going back to our very fundamental Ohm's law and KCL concepts only. All right, it's just that now we are applying it to a circuit with op-amp. So we just apply the golden rules of op-amp and get the node voltages and derive the current expressions from there. Okay, so that is basically how you solve for this, calculate the gain between V out and V in. Okay, so that is your final expression over here. Okay, so why is the blue not a ground? Because the positive is grounded. Okay, so if the plus is ground and the minus is also ground. Okay, any other questions? If not, let's go to the last question here. Okay, so in this question, okay, so V out minus this expression here is derived, okay, from the sort of direction that we have assigned for the KCL. All right, so we assume that all the current are flowing in to this node, and this node is ground. So V2 minus 0 over R3 is plus V out over 0, V out minus 0 over R4 will give me 0. Okay, so since this node here is considered grounded, okay, because V plus is grounded, so that is how we derive this expression here. Okay, when you are doing KCL, you are focusing on a particular node, correct? Okay, so if you remember the analysis like in NBA and so on, when we are deriving the expression for a particular node, we are only interested in the voltages and the resistance that are directly connected to that node. Okay, so that is the same sort of principle we are applying here. Okay, so the current flows out of the op-amp. Yes, current flows out of the op-amp, correct? But right now, we already have an expression for the voltage. Correct. Okay, so just like for example here, when you connect out a component to the output of the op-amp, current will flow, correct?
But right now, what we are looking at is in terms of what is the information we have. So even though current flows out of op-amp, there is no, uh, I mean, what we are interested in is this particular node voltage, all right, which relates to the V2, all right, and this voltage here, which relates to V out. Okay, so when we derive expressions, right, we are interested in, okay, which node are we talking about and how do we relate the components surrounding that node. Okay, and then from there we go on to the next step and the next step and so on. Okay, so current will flow out of the op-amp. Okay, so even though we say we have a voltage that is amplified, okay, but eventually when you connect up a circuit, current will flow. All right, but right now we do not need to worry about what current flows out of the op-amp because we know that we already have a expression for the voltage at the particular node here. So since we already know the expression for the voltage, that is enough to derive the other expressions connected to the other nodes. Okay, so let me go on to question 14 first, all right, and then other questions I'll come back to it later on. Okay. So question 14, derive the expression relating V out and the two inputs V1 and V2. All right, so this one again, we're going to apply the same concepts. So if V plus here is ground, then this is also considered ground. Okay. So with that, you can but this is already a normal inverting amplifier, right? This configuration here is a normal inverting amplifier. So your V out 1, actually you can just straight away get the answer that is equals to negative R3 over R1 V1. Okay, so that is your V out 1. Okay, because this first op amp 1 is already configured as a inverting amplifier configuration. Okay, now the next step is for, so you already have an expression for V out 1, okay, which is node 1 that captures the sort of effect of V1. Now we want to look at the effect of V2. All right, so we can create or look at another node over here, node 2. Okay, so at this node, let's do a KCL. Okay, and for KCL over here, again, let's apply the concept that since plus is grounded, this point here is also grounded. Okay, so if that point is also grounded, then you can say that this whole line here is considered one line, right? That means this whole thing is grounded. Okay, so all the current flowing in, okay, can sum up to 0. Okay, this whole thing is actually one line, which is one short circuit, correct? Because they are both connected together. Okay, so if I apply KCL at this node, I can say that all the current flowing in to that node will sum up to 0. Okay, so the expression will be V out 1 minus 0 over R4 plus V2 minus 0 over R2 plus V out minus 0 over R5 is equals to 0. Okay, so that is the expression by applying KCL to node 2. Okay, by applying KCL to node 2. So in this case, now what we can do is we can now simplify this further. So let me remove all the zeros first.
Okay, so V out 1 is given as this negative R3 over R1 R4 V1 plus V2 over R2 equals to negative V out over R5. Okay, so you can rewrite that final expression such that it looks like this: V out is equals to R5 R3 over R1 R4 or V1 minus R5 over R2 of V2. Okay, so you can see that right now your output is a sort of a difference between the two input voltages V1 and V2. Okay, but both of them now have a different scaling factor, right? Okay, R5, R3 over R1, R4, and this one is R5 over R2. Now, if I want both of them to be the same scaling factor, then what I can do, since R5, R5 is common, okay, I can look at this and this. Okay, so if R3 over R1, R4 is equals to 1 over R2, okay, that means the combination of R3, R1, R4 for this expression is the same as 1 over R2, then I can actually rewrite my expression to look like this, correct? R5 over R2 of V1 minus R5 over R2 of V2. Okay, so then I can just factorize out the R5 over R2 multiplied by V1 minus V2. So this R5 or R2 is nothing more than just a scaling factor K. Okay, so that is what the question asks us to do. That means show that the output is actually made up of the difference of the inputs multiplied by a scaling factor. All right, so in this question, we have also applied the same approach. Okay, we look at each or look at the different nodes to relate the output to the input voltage. Okay, so in our case, the output is V out, the input here is both V1 and V2. Okay, so we need to derive expression, okay, that have a combination of V out, V1 and V2. All right, so that is where the approach of defining nodes and applying KCL to the nodes comes in. All right, so when we create a node, for example, when I create this node, what am I trying to do? I'm trying to bring this variable here, V1, to another part of the circuit. All right, so V1 was originally on one part of the circuit, correct? But now that I create this node 1, now the V1 is now part of the VR1 expression. So V1 has been brought to another part of the circuit. Okay, and now what I want to do is I want to make sure that I have an expression that relates V out with V1 and V2. Okay, and to do that, I can now define a node where I can have expressions that involve V1, V2, and V out together. Okay, and then I do the solving. Okay, the same approach, if you look back at question 13, we did the same thing. Okay, what we want is we want to have an expression that relates V out to V in. That is the game. That is the aim of the question. Okay, so how do I do that? That means I first need to figure out how to bring V in to another part of the circuit where I can create an expression out of it. Correct. So that is why we first create a node. Okay, so this is V in. Then we derive an expression for current, and then we have one more node, okay, which is actually derived using the V in. Okay, so the whole idea of V2 is to bring V in into the picture. So when I bring V in into the picture, then I can now have another expression that can relate that node V2 with the V out, and V2 is already
expressed using V in. Okay, so when I simplify, I can finally get some relationship between V out and V in. Okay, so that is how you must approach the question. Okay, so we want to have this final expression that relates these two voltages. Okay, but they are both on different parts of the circuit. Right, so I need to use my basic principles, your Ohm's law, KCL, and so on, to derive expressions so that I am able to bring that V in to a part of the circuit that is closer to V out. Okay, and when I bring it to a closer part of the circuit is closer to V out, then I can apply maybe Ohm's law or KCL or something to have another expression. And then when I simplify the expression, I can solve the question. All right, so that is basically the idea that you must sort of understand. Okay, what we are trying to do. Okay, so when you understand that this is what we want to do, we want to bring the output and the input closer together into some part of the circuit. So that is where defining the nodes and the KCL expressions come in. Yeah. Okay, so that sort of brings us to the end of the tutorial questions. Okay. Yeah, so I will just stay for or anything that you want to ask and clarify. All right, regarding these questions. Okay, if you have nothing to ask, then you can log off. All right, if not, I will stay on to answer. Okay, so the question: why will V out be affected by op amp 1? Okay, so the effect of op amp 1 on V out, okay, is already captured through the expressions that we derive. Okay, so see, when V out is actually here, this is also V out because they are all the same line. All right, so there is no sort of difference between the op amp 1 and V out. So V out is actually the output of op amp 1. All right, and what we are trying to do is we are trying to see the effect of the V in together with the combination of op amp 2, okay, on the output that we get on V out. All right, so no matter how the circuit is, as long as you follow the same principles, that means you want to derive expressions that allow you to bring your voltage V in or V1 or whatever to another part of the circuit. From there, you can derive expressions that can again be used to simplify and get the final expression. Okay, so as long as you follow the principles, then I think you should be able to do it the same way. Okay, so the question is, the output current op amp 2 does not matter. Okay, so the output current flow, there is a current flow. All right, and this current flow, okay, how much, what is the actual value? We do not know. Okay, what is this actual current? We do not know. All right, but what we know is V2. Now, is this current going to affect V2? No, because there is no voltage drop over here. Correct? There is no current, there is no resistor directly connected to the output of the op amp 2 here. So if there's no resistor connected to the op amp 2, then your okay, so even if, okay, let me put it this way, that even if there is something else over here, all right, what we do know is this: if you are applying KCL to this node here, okay, if I am applying KCL to this node, okay, in this particular node, the KCL expressions are formed by three branches, correct? This branch, and this branch. So my KCL expression will not change. All right. Now, will V2 be affected by anything else by op-amp 2? It will not be affected. Why? Because we know the current here. And we know that this same current is also the current that is flowing here. Okay, which means that by Ohm's law, all right, the voltage drop across R2 is based on the same current I, which is flowing through R1 and R2. So the V2 value is already known because that is the current that is flowing here. Okay, so this current, okay, is a combination, okay, could be a combination of the op-amp 2, okay, the V out, okay, or whatever, we do not know. But what we know is the voltage at this point is V in, and with that we know the current going through R1. Okay, so since we know the current going through R1, we can also say for sure the current going through R2. And with that, you can also say for sure the voltage at V2. Correct? Because this voltage here at V2, okay, is dependent on the voltage drop of the components from that until ground. Correct? So if you imagine that if I draw this circuit separately, okay, let's say this is V2. Okay, so let's assume there are other components here. Okay. Okay, and some other circuit, doesn't matter. But from here, I know that I have one resistor and I have another resistor. Okay, and I know that this is VA and this is VB. So no matter what I have here, that is a separate issue. V2 will always be VA plus VB, regardless of whatever else is happening there. Because the voltage at the point is with respect to ground. And with respect to ground, I have two resistors. So the combination of the two voltage drop will always give me V2. Correct? So if I know V2, then of course I can now go on to extend and find maybe other currents and other voltages and so on. Okay, so Y V out is minus R3 over. Okay, so this is just inverting amplifier. Okay, even if you want to go back to first principles, okay, you can do it the same way. So if you take the current flowing in is the current flowing here. So this current flowing here is V1 minus 0 over R1, which is the same current flowing here. All right. So the current flowing in this branch here is given as 0 minus V out 1 over R3. Correct. So if you equate the two together, V1 minus 0 over R1 equals to 0 minus V out 1 over R3. Then you will get that V out 1 is equals to negative R3 over R1 V1. Okay, even if you go back to the basic approach to deriving the current expression, you'll get it. But like I said, if you look at it already, you can see that this is an inverting amplifier. So inverting amplifier, your V out is negative RF over R1 or RI multiplied by V in.
Prof, sorry, then like actually I'm like super lost on this question. So it's like, do you mind you can go through starting from the green color question? Yeah.
Which part? Which part?
Like
So the first part is the inverting amplifier, correct?
yeah. So that one I understand already by the first principle. Then after that I like super lost on this question.
Okay, so if you look at this node 2, okay, so this is basically a node, correct? Okay, we are defining this node, okay, to derive a KCL expression here. All right, and
Like,
we are
sorry,
basically, huh?
as in like I noticed that you like highlighted that line, right? Then it's like, if I'm not wrong, is it the whole line is grounded?
Yes,
Like, why is node 2 also grounded?
because node 2 is connected to this node. It's a short circuit, correct? This two
Oh,
is a short circuit, correct?
yeah.
It's just a piece of wire. So that means if this point is grounded, then node 2 is also grounded, correct?
Yeah.
So now the next step is we want to create a KCL expression for this node over here. And when we create the KCL expression, basically what you have is VR1 minus ground. Okay, so if you think about it, like so you have VR1 R4. Okay, this is your common ground here, and then you have your V2 with R2, and then you also have your R5 with your V out. Okay, so now we are saying that we are deriving expressions for all three currents going into this node.
Okay.
So this expression will be V out 1, so it's minus 0, so it's just V out 1 over R4, and this is V2 over R2, and this is V out over R5. Correct?
Yes, okay, so this one I understand. Then after that, the next sentence.
So the rest of it is just simplifying, correct? So from here to here, you are just grouping together and simplifying.
Like when you get the R3 over R1 times R4, like that part, is it from,
No, R5, we cross multiply across both.
as in how to say it, like 1 over R4, how to say, like from the first green sentence to the second green sentence, like I noticed that the change is like the R3 over R1 times R4, right, for
Yeah,
V1.
because your V out 1 is defined here, correct? So V out 1, I'm now replacing it in
Oh,
terms.
okay, yeah, okay, I saw it, yeah.
Then the next step, I take R5 and I cross multiply across both the terms.
Oh, okay, yeah, okay, I saw it.
So after you cross multiply, then you have this expression, correct? So when you get this expression, what you have is, you can see that it is V1 minus V2, but the scaling is different, correct? So in order for us to say that it is a common scaling factor, this condition must be fulfilled.
Wait,
So
sorry,
this condition,
what's scaling factor? Like,
in the question, they say they want it to be multiplied by a scaling factor, correct?
oh, gain factor, yeah.
Yeah, so scaling factor means just you a common number, again. That means the V1 minus V2, I double it or triple it or something like that. Correct? It's just a number. So if I want the number to be the same, that means the scaling factor in front of V1 and V2 must be the same. So in order for that to happen, this condition must be fulfilled. So since R5 is already a common term in the numerator, I can look at 1 over R2 to be the same as R3 over R1, R4. And if that condition is fulfilled, then on the scaling side, what I have is both of them will have R5 over R2.
Like just to clarify, like how to say like this thing, right? Is it like the V out equals to A then bracket V1 minus V2, something like that? Okay, okay, now it's like how do I say this? Like if I'm not wrong, you are equating like the coefficient of V1 and V2 to be the same, right?
Yes.
Like how do I say this? Like
Okay,
it
so
is the same because
basically what I'm saying is this. Okay, so maybe okay, what I want to say is, okay, I want both of this to be the same. R5, R3 over R1, R4. I want it to be the same as R5 over R2. Okay, I want this both to be the same. Then they both have a common scaling factor, correct? Okay, so if let's say now I factorize out this, then what do you see? You see that R5 and R5 are common. Left is, sorry, this is 3. So this and this must be the same, correct?
yes.
So if both of them are the same, then they will both have the same scaling factor.
Then can I ask, like you equate them to be the same? Like is it like it's like what's the reason? Like is it because V out is always 0?
No, we equate them to the same because the question wants us to have a common scaling factor.
Common scaling factor.
They said they want it to be the difference of the input voltages multiplied by a scaling factor, correct?
The V1 and V2, they are the input voltages. Okay, so they want the, sorry, can you repeat the last sentence? Like
No, the question says what? Can you
they
look at the
want,
question?
yeah, they want like the amplified by a gain factor.
Yes. So the gain factor should be a common gain factor that is applied to both V1 and V2, correct? Because you already have the difference here, that it is now the difference between two voltages. Okay, but I want to make sure that they are both the same scaling factor. So the scaling factor means the resistor combinations must be chosen such that the V1 and V2 are both changed or amplified by the same amount.
Oh, okay. Yeah, I think I kind of understand. So if I'm not wrong, then the gain factor in this case is the K, which is alpha over R2.
Yes.
Okay. Oh yeah, then sorry, then can you just scroll down a bit? I want to copy the, yeah, okay. Yeah, okay, thank you.
Okay, so anything else anybody want to ask? Okay, so nothing else. That's it. You can end today. I'll see you all next week for the studio.
Wait, then sorry, then like the R3 over R1 times R4 equals to 1 over R2 that we have derived, right? Then it's like, if I'm not wrong, we just use either the 1 over R2 or the R3 over R1 times R4, right?
Yeah, so the requirement is R5 over R2 is now the new K, correct?
Yeah, so it's like if I were to put
R5 is a fixed value, correct? So that one it applies to both V1 and V2. So the only thing that is left is when you choose your R2, R1, R3, and R4, they must agree to this condition here.
so if I were to put R5 times R3 over R1 times R4, also correct, right?
To be equals to R5 over R2 lah.
because you want both of them to be the same, correct? Okay, so the condition is both of them must be the same.
Yeah. So it's like since so it's like then I use if I use the left side one, it's also correct. Yeah,
you can use the left side also to find, but then you must just make sure that the R5 is the common term.
the
The only variation is that the R3, R1, R4, R2 must agree to the relationship there.
Okay, understand.
Hmm.
Thank you, Prof.
Okay.
Bye bye.
Bye.